All right. So VSEPR theory stands for valence shell electron pair repulsion. That's not something you need to memorize. What you do need to know is how to use VSEPR theory to predict shape or molecular geometry. And so the first thing we need to cover is AXE notation. All right, so AXE notation is essentially the first step to predicting a molecule's molecular geometry. The A stands for the central element, X represents bonded atoms, and E stands for lone pairs. Now the N and the M represent the number of bonded atoms and lone pairs respectively. And for every molecule that you're given, if you're asked for the shape, the first thing you should do is to write the AXE notation. Now, the AXE notation can be used to figure out the geometry. There's two types of geometry. There's electronic and there's molecular. Electronic's the easier one, where it depends solely on the total number of stuff or things attached to the central element. And by things, I mean either a lone pair or a central atom. So if there are two things bonded to the central atom, it's linear. If there are three things, whether it's three bonded atoms or two bonded atoms in one lone pair, it's trigonal planar. If there's four, tetrahedral, five, trigonal bipyramidal, six, octahedral. Molecular geometry is the more tricky one, where there's a lot of different options. Each AXE notation corresponds to a different molecular geometry. This is something you should memorize. This will not be given to you on your exam. And you should also know the bond angles. While I would suggest using flashcards to memorize this, I think it might also be a good idea to use your molecular model kit to help you sort of visualize each of these structures, and that will help you remember them on the day of your exam. All right, so let's try to write the AXE notation and electronic and molecular geometries for the following. So let's start with H2O. So the first step really is to draw the Lewis structure, and before you draw the Lewis structure, you need to count number of valence electrons. So we start with hydrogen, right? So hydrogen has one valence electron, but I have two of them, so that gives me 2 electrons. Oxygen has 6 valence electrons, and so in total I have 8. Remember that hydrogen can never go in the middle, so I put oxygen. Attach it to these two hydrogens with single bonds, and I give a full octet to the central element, and there I've used 8 electrons. This guy is going to be A, X2, because there's 2 bonded elements, E2, because there's 2 lone pairs. The electronic geometry, just remember that that depends only on how many regions of electron density are around the central element. And a region of electron density is either an atom or a lone pair. So in total, there's 1, 2, 3, 4. And so anything with 4 things around it is going to be tetrahedral, whereas the molecular geometry is dependent on the AXE notation. So then you look at your chart, AX2E2 corresponds to bent. Right? And so that's H2O. We can do the same thing for NH3. So the first step, count valence electrons. Nitrogen has 5. Hydrogen has 1 times 3 is 3 valence electrons. I add that together, I get 8. So what's going to happen is nitrogen's going to be in the middle. I attach to 3 hydrogens. And that extra lone pair on the nitrogen, I've used 8 electrons. This guy is going to be AX3E because there's 3 bonding elements in 1 lone pair. And the electronic configuration or geometry is going to be tetrahedral because there's 4 things attached to the central element, whereas the molecular geometry, which is dependent on AXE notation, will be trigonal pyramidal. Trigonal pyramidal. And again, as I mentioned, if you do have a model kit, go ahead and make it and you'll see why it's called a trigonal pyramid. So let's do ClF3. All right, so chlorine has 7 valence electrons. So does fluorine, but I have 3 of them. So that gets me 21 valence electrons for a total of 28. The less electronegative element goes in the middle, which is chlorine. And so I attach that to 3 fluorines. And then my next step is to give all the non-central elements a full octet. And so those are my fluorines, right? And so basically to each fluorine, I give 3 lone pairs. And in total, I've used 24 electrons at this point, but I have 28. And so for the extra 2 lone pairs, I put them on the central atom. And here notice that chlorine has more than 8 electrons around it. That's okay, because it can accommodate an expanded octet. And so here the AXE notation is going to be AX3E2. The electronic configuration, geometry, excuse me, is going to be trigonal bipyramidal, because there's 5 things attached. Trigonal bipyramidal. And the molecular geometry is going to be T-shaped. All right, and then so the last one we'll do is ICl4 minus. So we count valence electrons. I has 7. Cl has 7 valence electrons. There's 4 Cl's, so that gets you 28 plus 7 is 35. And then I add an additional electron because of the negative charge, so that gets me 36. And so I goes in the middle. I attach it to 4 chlorines. My next step is to give all the chlorines a full octet. And after I've given all the chlorine, each of the chlorines 3 lone pairs, I've used 32 valence electrons. And I have 4 electrons left, 2 lone pairs left. I put those 2 lone pairs on the I. And it's okay because I can accommodate an expanded octet. This guy has 4 bonds, so it's going to be AX4, 2 lone pairs, E2, right? And so the electronic geometry is going to be octahedral because there are 6 things attached. And the molecular geometry is simply going to be linear. All right. So the second thing that you'll have to know how to do is determine whether a molecule is polar, right? And so if a molecule does not have polar bonds, it's not going to be polar, right? So that's the easy case. If it does have polar bonds, then there are 2 requirements for it to be nonpolar, right? And so the first requirement is for all bonded atoms to be identical. The second requirement is that the molecule needs to be symmetrical. And the reason this is important is because those polar bonds, those dipoles, need to be able to cancel. And it turns out these following shapes, these 8 shapes, are the only ones that are symmetrical. And so if ever you have a molecule that has one of these 4 shapes and has has all elements, all bonded elements being identical, then you have a nonpolar compound. And just as a reminder, you need both of these requirements for the molecule to be nonpolar and for the dipole moments to cancel, right? So let's classify these molecules as polar or nonpolar. So let's draw these Lewis structures. So we already drew these in the previous slide, but basically H2O looked like this, right? It had a Lewis structure like this, and its AXE notation was AX2E2. Now here the bonded elements are identical, but bent is not a symmetrical shape, and so we say this is polar because the dipoles will not cancel, right? NH3, right? We did the Lewis structure before. The N is bonded to 3 hydrogens. The AXE notation is AX3E. That is not symmetrical. It's not one of the 8 symmetrical elements. This should be an N, and so that's going to be polar. ClF3, right? We drew that before, basically with the chlorine attached to these 3 fluorines. Each of the fluorines has a lone pair, and then there's 2 lone pairs on that central chlorine. Now, this guy had an AXE notation of AX3E2, which is T-shaped, which is not symmetrical, and so this guy's going to be polar. And then finally, this guy, if you remember, it had 4 Cl's attached with lone pairs around each one. And then 2 lone pairs on that I, which means that it was AX4E2, which is linear, is symmetrical, and therefore nonpolar. Because only in this situation do the dipoles cancel. All right. So the last thing we'll talk about is hybridization. So hybridization is an important topic. Really, what you need to understand when it comes to hybridization is how to identify whether an atom is sp, sp2, sp3, sp3d, or sp3d2 hybridized. And all you need to look at is the number of attachments around each atom. And so and by attachment, I mean anything that is either a bonded atom or a lone pair. So sort of it's like a region of electron density. So if there's two things attached, it's sp. If there's three things attached, sp2, and so forth. And the reason atoms form hybridized orbitals is because they're more stable. All right, so determine the hybridization of the central atom in the following, right? So H2O, right? We drew the Lewis structure a few different times now. So the oxygen, remember, had four things attached. It had the lone pair, and it had the hydrogens. So there's four things attached. That's going to be sp3. CH2O, right? This guy will look like this. There are hydrogens, and then there actually needs to be a double bond. You'll realize this after you count total number of valence electrons, but there needs to be a double bond here. Here there are three things attached. The double bond is not, you don't count the double bond twice. And so basically there's 1, 2, 3 groups attached. You call that sp2. ClF3 had a total of 5 things attached. And so we call that sp3d. And then ICl4 minus had 4 Cls attached and 2 lone pairs, total of 6 things. And so that's going to be sp3d2. And so that's really all you need to know for hybridization.